So this is the original motor that we had. It was a toy motor kit that was given to us on the first day of class. And our biggest problem with that was getting even connection between the stator magnet and the rotor magnet. So that was one of the key factors that led us to switch to using permanent magnets so we could get optimal connection to our rotor. We don't have the kit, we don't know where it went, but we based all of our further design plans on that one sole property.
For our first iteration motor, it was very similar to this one, but only had 2 poles, and that was the one we used the 30 gauge winding wire on. So for this one we wanted to be able to increase the number of turns, so we made a 3-pole so that we could get more windings on. And we also increased the wire gauge to the 24 so it could handle more current.
As you can see from here, parts of the coil did actually fall off because we got this thing to such a high RPM that it couldn't handle the reaction force generated from the centripetal force. So we had to go back to square one and not only redesign our brushes, but our entire rotor. As you can see, compared to the other model, we actually put these blades on here to actually keep these coils from actually falling off of our rotor again when testing. That was a huge improvement. And if there's one other thing we could improve, it's just the number of turns on each pole.
So some of the key features to this design were the ball bearings. They made a big difference over the last generation because there was no play when the motor spun, and it allowed it to spin a lot faster with less friction. So for a commutator, the biggest goal was just to make the highest amount of contact at all times. So we made sure to solder on little pieces of copper wire at the ends of the wire winding so that we could get a better contact surface between the commutator and the brushes. Okay, so this is our third iteration motor. Some of the modifications we made from our last motor here were we upgraded the brushes, the contact that the motor makes with the brushes. From this one we just had pieces of the copper wire that we took the enamel off the ends connecting to the commutator. This one we had a couple attempts. We first tried using these pieces of copper wire that we pounded down to make kind of flat surfaces to have a better surface area and make better contact with the commutator. And these worked well, but then we ended up upgrading these to these brushes that we got off our own motor, some motors that we found in spare parts, and we found these made a lot better contact, and as they wore down they kind of made a better surface area against the commutator. Another difference we made in this motor was we went from a 3-pole to a 4-pole motor, and we weren't sure if this would be faster or slower or what the characteristics would be. We also put, instead of just a single magnet on the bottom, we added 2 magnets, one south pole and one north pole. And one of the biggest modifications we made was a better design opposed to our last one, which had a lot of play in the shaft and it made the brushes lose contact. So this one, when the brushes aren't creating friction, it spins very freely, and just the magnets are the only thing that kind of causes it to slow down. So that was a big difference. Similarly to the last one, we used pieces of small pieces of copper that we pounded down and soldered to the ends of the windings as the brushes. Because this is a 4-pole, we have 4 brushes. Only 2 are connected at a time. And we used some 24 gauge copper wire again. We found that this worked the best. We had experimented with some smaller gauge. We initially used some 30 gauge wire and found that it could not handle as much current. And when we were going through the equation of the force is equal to the number of turns times the current, so we wanted to be able to have a lot of current through the windings. Each of these poles has about 100 windings around each one, times the four poles. So we're able to have a lot of current flow through there, and when the motor runs, we get about 10 amps max at 6 volts. So I'll first show the motor on at 3 volts running. And up to 6 volts. So one of the big improvements we found that could improve this motor, or something we could have improved on later, is that the motor continues to go faster with when more pressure is on the commutator, when it's making a better connection. So we used a piece of tape for a final test, and we found that it did run a lot faster. So it's 6 volts. So with this, we kind of figured out that it'd be best if we had good contact between the brushes and the commutator, which we've seen on rail motors. They'll sometimes use springs to be pushing the brushes against the commutator, and we didn't end up having time to figure out how we could introduce like a spring to be holding the brushes together so that they always had stronger contact. Because kind of, as you could see, it runs much better the tighter it is, and even with the tape and while holding it together, it ran a lot smoother and faster. With the tape on it, using the stroboscope in lab, we were able to get the motor to 3,300 RPMs, which was pretty fast, and that was a lot faster than without the tape. That was more like 1,200. Another modification we made was putting the magnets a little closer on this one, opposed to the last one. We tried to limit the space between the air gap between the magnets and the electromagnets on the motor, on the commutator, and we found that made it go faster too. So what we did was we had another revision of this motor where the shell was kind of farther apart, and we just continued moving, making the shell kind of tighter until the motor ran at what we thought was the best performance. And we found that if it was too close, then it required too much torque, and the motor didn't really have the power to spin without getting caught up on the magnets. So we found this to be a good distance between them. So here's a diagram of how our motor is going to be working, or how it did work. We had the magnets on the north side with the north pole and the south side, south pole, and of course the flux density will then move from north to south, and depending on the way that we energize the coils from the DC voltage in will determine the direction that the motor spins. So if we were to energize it positive on this side and negative on this side, as the voltage goes into the coils, it's going to touch with the brushes and it's going to energize two of the coils at a time. So when it energizes one set of coils, they're going to both either be pulled or repelled by the permanent magnets, and they're both going to be opposite from each other, so that was what will cause it to spin. One side will pull, one side will push, and it will keep alternating. Every time it changes where the brush is, it will change which of the four poles is energized.
And we basically just use two simple sets of equations to try to get the maximum RPM. Was first our magnetomotive force equation that says that the magnetomotive force is equal to number of turns times the current. The current, we pretty much had control over just the gauge wire we used, so the lower gauge wire we used, the more current we saw drawn from our motor. But the biggest factor that we can manipulate was the number of turns, and that's why we went with the 4-pole setup, to try to put the maximum number of turns on 4 poles.